Alrighty guys, so question 14, we're going to complete the mechanism for acidic hydrolysis of the ether shown. And so with these problems, it's all about mechanism, all about really knowing how to show your arrows, how to understand what step is going to be occurring next. The nice thing is that there's a lot of hints everywhere. So it tells you you're going to get a protonated intermediate here, it tells you you're going to be doing an SN2, you're going to get your SN2 product, you're going to protonate an intermediate again. And so the hints are there to help you out. And so let's go ahead and run through this one, talk about what's happening, why it's happening. If I can figure out how to get this to work. There we go. All right, so very first reaction that we're going to have here is going to give us our first protonated intermediate. So as it's going to be a protonated intermediate, that means it's going to have a positive charge. The only thing really here in this compound that would want to be protonated is going to be the nucleophilic oxygen that's here. And what makes it nucleophilic is the fact that it has lone pairs. And so the oxygen has two pairs of lone electrons that are looking to grab onto something. So in this case, we're doing sort of an acid-base reaction where these electrons, make sure you start your arrow at your electrons, are going to be grabbing onto that hydrogen and protonating that oxygen. And so always make sure to also draw the fact that that hydrogen is going to leave some electrons with that bromine, which is what makes the bromine negatively charged. And so now that we've got that is going to give us our first protonated intermediate. We haven't done anything as far as starting to rearrange the compound. We're just going to get our protonated intermediate, which is going to look like this. Okay, so we grabbed onto that hydrogen using the oxygen, which now gives us 3 bonds on the oxygen, overall making it protonated or positively charged. And so that's our first protonated intermediate. Okay, now our next step, we're going to be doing an SN2 reaction with this bromine. So a substitution reaction, we're going to be losing a leaving group and attaching that bromine. That bromine is our nucleophile. It's going to be attaching onto the compound. So you might be asking yourself, well, where's our leaving group? There's no bromine, iodine, there's not even necessarily water there. So what's our leaving group? And our leaving group is going to be that oxygen because it's positively charged. So it wants to leave and take electrons with it in order to balance its positive charge out. And so it can actually do that through 2 directions. And those directions are either take these electrons being shared here or take these electrons being shared here. So now you might be asking yourself, well, how do I know which direction to choose? And the resultant of this is you're going to get you're going to, 1, break the ring first off, and 2, you're going to get an alcohol that's going to be hanging on to the compound. And so that alcohol needs to be the most stable alcohol you can get. And so you're going to break it in the direction that's going to give you the most stable alcohol. If we were to break this bond here, that means we're going to give those electrons to this oxygen, ultimately leaving that oxygen, that now a hydroxyl group, on this carbon, which would make that alcohol a tertiary alcohol. If we were to break the other direction, where we give these electrons onto the oxygen, we are now leaving that oxygen and hydrogen, that hydroxy group, on this carbon, which would be a primary alcohol. And so that allows us to determine that we're going to be breaking this bond here, allowing the hydroxy group to become a tertiary alcohol, which is going to be more stable. And when we break that bond and give the electrons here to that oxygen, it's going to cancel out that positive charge. Now this is an SN2 reaction. So remember, SN2 reaction has 1 step. So the way I remember it is SN2, 2 to 1, 1 step. SN1, 1 to 2, 2 steps. Okay, regardless. So when that leaving group is leaving, when that bond is being broken, at the same time, in 1 step, we're going to be having the bromine attack from the back. and attach onto that carbon that is losing those electrons. So if we were to have kind of the transition step, or the step that's in between, is we'd have something that kind of looks like this. The oxygen and hydrogen are now happy with those electrons here. And then here we would have now a carbocation. So that's where the positive charge goes until we attach that bromine. And so once we do attach that bromine, we'll get our SN2 product, which is going to look like this. All right, and so something to note here is that in purple are the elements that are being added onto the original compound, which is in red. And so in our first protonated intermediate, we grabbed a hydrogen from the hydrogen bromide and attached it, so that's why that is in purple. And this time we're attaching a bromine onto the compound, and that hydrogen that we first added is still there. All right, so we've got our SN2 product, and now the hints are telling us that we're going to be having a second protonated intermediate. Now we're going to do the same thing here that we did the first time. We're going to protonate the oxygen. And so generally when you see that you're protonating, and when you're going to have a protonated intermediate, it's usually pretty safe to infer that the oxygen is going to become protonated by something. In this case, we're going to be doing the same thing, where we're going to take one of these lone pairs and grab onto the hydrogen over here. Make sure that you show another arrow representing the hydrogen leaving its electrons behind with the bromine. And so when we do that, we get our second protonated intermediate. Which is going to look like so. So now notice that we have the OH2, which is H2O, water. Notice that we have two hydrogens in purple, meaning that we've added two hydrogens to the original compound, and that makes the OH2 a good leaving group. And so now that's actually what our next step is calling for. It wants the elimination of the hydrogen. So when you see a negative with a compound, it's representing that you're getting rid of that compound from the ultimate base compound. So in this case now, what that's saying is our leaving group is leaving. Leaving group leaves, and that will form a carbocation. So that's what our next hint was, is you get a carbocation intermediate. So we're almost done. Hopefully you're feeling pretty good about this. And if not, I actually just, I'm currently in pharmacology, and I was learning some stuff about the basal ganglia and the substantia nigra, and I was watching this really good review video, but I had to watch it about 5 or 6 times before I really felt like I understood what was going on. And so that just might be the way you have to do it as well. Hopefully these review videos are helping you out. If not, always definitely look into secondary resources. But let's keep moving forward. So now this carbocation intermediate, we're going to do an SN1 reaction that's going to attach the bromine. And so that makes sense that we're doing an SN1 reaction, because that happens in 2 steps. Remember, 1 has 2 steps, whereas 2 has 1 step. And so this SN1 reactions, those are 2 steps in the sense that they form a carbocation, and then you want to look for some rearrangement. In this case, we're already a tertiary carbocation, so we're not going to rearrange anything. If we were secondary and there was a tertiary next door, then yes, we would do something, but in this case we are good. And so our final product is going to just very simply be that this bromine, this negatively charged bromine, is going to want to add onto that positive charge. It's going to balance out, and that'll give us our final product. So drawing that ahead for you here. And so this is what our final product looks like. And so you can always double check your answer with a formula that's given Always double check your EU so let's do the EU of this one. I'm just going to do it real quick the way I do it. So 7 carbons times 2 is 14, plus 2 is equal to 16, minus 14 hydrogens is 2, minus 2 halogens is 0. So we have an EU of 0, meaning we're not going to have any double bonds, any triple bonds, no rings, and so in this case we are good. If we had gotten an EU of 1, we would have been concerned, maybe thinking that we had to form a ring in some part of the mechanism, but in this case we're solid. So hopefully that helped out, guys, and good luck on your exam.